Okay, so till now, if you look back all the lessons, we always work with one single pump, right? Even in PyFlow or even these initial lessons of pump flow, we always used one single pump. Now, for some reason, if one pump is not enough, we can work with multiple pumps. Just like the PyFlow, we can add pumps in series and in parallel. Now, that's what we will discuss for next two classes. The first thing, we will discuss what is pumps in series, what is pumps in parallel. And in next part, we will discuss how to determine whether we need pumps in series or parallel. Okay, that's what we will do. Now we have, like I came up with two case studies here. Here. So for both cases, like we have two case studies here, we will discuss those. So for both cases, the project manager has two pumps already in the site, okay? And the pump characteristics are given below in this table. So this is pump A. This is the Q versus HA. And this is pump B, okay? Q versus pump B. And you can see they are not identical pump. They have different characteristics, but they have kind of similar head for the same Q, okay? Now, for case study 1 and case study 2, the project manager has to deal with that, like how he or she will work with these available pumps, because they don't have time or money to buy a new pump. So they don't have any money left for the project still, and they don't have the time to go to the market and find the exact pump. So they have to work with these two available pumps. Now the question to you is how the project manager can work with these two available pumps for the following cases. Okay, so case study 1. Can someone read the case study 1 very quickly?
A pipe system having a total static head of 80 feet has a supply of 1,050 GPM water from reservoir 1 to reservoir 2. The pipe comprises a 6-inch diameter pipe of 100 or 1,200 feet length with a minor loss of 20 times velocity at F equals 0.022.
Okay, thank you very much. So we have two open reserve, like the project manager has two open reservoir system there, okay? And the system has to supply 1,050 GPM from reservoir 1 to 2, right? Now, the system curve is already given here. We know the system curve, the general expression for system curve is H pump equals to delta Z plus head loss, right? We know that. Now, from the question statement, you already know the total static head is 80. So that's why 80 plus 29.3 Q square. Now, your task for this specific system, can you tell me for 1,050 GPM, what will be the pump head? I'm giving you the equation here. 80 plus 29.3 Q square. So we are looking for the pump head 1,050. Is that correct, or we need to do something? We need to do the unit conversion. Great. Because we can't work with the GPM, we need to convert that equation flow to CFS. Okay. So this 448.8, it's within the parentheses, so you need to square that. So give me the pump head for this specific case. What number you got? 240.3 feet. Okay. Anyone else got? Okay. Now that simply means To supply that 1050 GPM for that specific system, you need to provide 240.3 feet of head, right? Now let's check for a single pump if we can get that. So for pump A, what is the maximum head for pump A?
186.
Okay, that is the maximum. For pump B, what is the maximum head?
172.
Now you see for any of these pumps, there is no head which is close to 240.3 feet, right? So these two pumps can maximum add 186 with the zero capacity. So that is the maximum head they can add. So for this 150 GPM, there is no way one of these pump can add 240 feet. That simply means the project manager can't work with one single pump here. He or she needs to come up with something, right? Okay, that is case study 1. I will just stop here. So they need more head because one pump can't get that much head. For case study 2, here, something similar to that, but this time the system has to supply 2100 GPM from reservoir 1 to reservoir 2. And this time the system curve is HP equals to 40 plus 4.39 Q square. So let's check 4.39 Q square. Okay, so let's check for 2100 GPM. What is the head this system? 448. That is the conversion factor from GPM to CFS. So the actual conversion factor is this one. 1 CFS equals to 'Does that answer your question? Okay. Okay. So what is the pump head you got from this one? 136.1 feet, right?
Yes.
Now let's check the pump A again. What is the maximum capacity pump A can give you?
186.
Maximum capacity or discharge.
1400.
The same thing for pump B also, right? So pump A can give you 1400, pump B can give you 1400, but you need what? 2100 GPM, right? Now, if you look from the head perspective, 136.1, so 136.1 will be somewhere here, right? And the head is maybe 1300 GPM. And for this one, 136 will be here. And what is the flow here? 910,000, 10,000, something like that, right? You see, even for 136, you are getting only that much of flow. For this pump, for 136, you are getting 1300 GPM. So in any way, again, one pump is not enough for this system, right? Now, since the project manager doesn't have time or money, there is no way they can buy a new pump. So they have to work with these two pumps, okay? Now, there are two ways. Either they can add the pumps in series, like one after another, or they can add these two pumps in parallel. Now, the project manager has to decide how they will add the pumps together, whether in series or parallel. How to know that? They need the basic principles to know, like if they add the pumps in series, what will be the benefits, and if they add the pumps in parallel, what will be the benefits, right? So that's what we'll discuss for today's class for first few minutes, and then we will do some calculation to check whether these principles are correct or not. Okay, so let's do that. So pumping in series and pumping in parallel, this is kind of the schematic diagram here. Now I need to let you know one thing. In this picture, you see these pumps, they are located in different elevation, right? But those who went to the lab on Monday, did you see that the pumps were in the same elevation in our lab? You saw that, right? The pump was on the floor.
Yes.
So that doesn't matter. Like where the pumps is situated, it's like it matters, but it not like that it has to be on different level. They can be on the same level. That's how the pump characteristics curve will be adjusted. Okay. Now for pumping in series, it's like this is the pump A, this is the pump B, this is 0.1, this is 0.2. So pump A is adding head HA, and from this point to this point, this pump is adding a little bit more head. So finally, what is the total head? HA plus HB, right? Now, are you seeing any other source of water after the pump A location? Is there any other source of water? There is not. That simply means they are actually carrying the same Q, right? So Q equals to QA, QB. Does that make sense for the pumps in series?
Yes.
Okay. Now for pumps in parallel, again, I will name the pump as pump A, pump B. Now this time, if you look at these two pumps, they both have a water source, right? Like from that source, these two pumps are drawing some water. So this is QA, this is QB. If that is 0.1 and that is 0.2, what is the elevation difference for pump A? In between A1 and 2, it's HA. For B, what is the elevation difference in between 1 and 2? So they are same, right? That simply means pump head equals to pump A. It's same. Now, what about the flow? And if I want to find the total flow, how can I do that? Yes. You see, you know the principle here. We just needed to discuss that, right? So that simply tells you. Now my questions to you, if I need more head or more height in the system, should I add the pumps in series or parallel? In series, because I'm getting more head. Now, if I need more flow for any system, maybe for agricultural purpose, the height is not that much, but I need huge amount of water. What should I do? Should I add the pumps in series or in parallel? So it should be parallel because it is giving you. Okay. So these two are the important things to understand for pipes in series and parallel. Now I will give you one more example. just for better understanding. Hopefully you will find that useful. But are you done up to this point, everyone? In these rows, are you done, everyone? Okay. So let's do one more practice here. Pumps in series. So what I will do, I will use a metaphorical example, something like that. So this is the ground floor of NEB, okay? And this is the stair, first floor, second floor, third floor, 400 level, okay? So up to this point, this is the first floor. This is the second floor. This is the third floor. And this is the fourth floor. Okay. Now we have one bucket of water, 5 gallon. Okay. And we have one cadet here and one cadet here. Now you need to take the stairs because you are not allowed to use the elevator. Okay, so you will take the stairs to carry these 5 gallons of water. Okay, now this cadet, he or she will carry these 5 gallons of water from ground level to second floor. So what is the elevation? This bucket is like traveling from ground floor to second floor till now. Suppose for each floor it's kind of 10 feet. So this gallon is traveling from ground floor to second floor. What is the elevation this gallon travel so far? Up to second floor. 20, right? Okay. Now from second floor, another cadet will carry the same bucket, and she will take that bucket to 400 level. Now, how much elevation is added? Okay. So total elevation is what? But what is the total amount of water which is being traveled? Say 5 gallons, right? That means the same Q is traveling from point A to point B by 2 pumps or 2 cadets. So you are having more head, or you're traveling more height, right? So this is kind of like relay race. This cadet is passing something to the next one. Okay, and if you look at the pumps in series, they are kind of same thing. And this is HA and this is HB, and in total that is HA plus HB, but the Q is same, right? Okay, now the next case scenario, again, here it's the ground floor, and I have the same staircase, 1, 2, 3, 4. Okay. And this time I need to carry 2 buckets. Okay. And obviously one cadet can't take 2 buckets at the same time. So what I thought, okay, maybe I will ask both of them to come to the ground floor and carry this bucket. Now, this one is one cadet, and you will check the stairs again, no exception. Okay. Now you do that, 1, 2 here. both of them are carrying 5 gallon because each cadet can only travel 20 feet, not more than that. So both of them are going from ground floor to second floor. So what is the elevation they travel?
20 feet.
In real, they only travel 20 feet, right? Like the 20 feet you can use. Now, what is the flow travel from ground floor to second floor? They both carried one bucket. So in total, you got what? How much of water?
Yeah, 10 gallons.
10 gallons, yes. So exactly same thing here. This is one cadet. They both are carrying 5 gallons. 5 gallons, okay? But they are only traveling this 20 feet, right? So they are working in series or parallel?
Series. Sorry, parallel.
They're working parallelly, right? Okay, so just the main point to take from my last 30 minutes lecture is if you need more head, you will add the pumps in series. If you need more flow, you will add the pumps in. Finally, my 30 minutes lecture is done. Okay, now we can do some mathematical problems, but you need to make sure that you know this one. Even if you can't remember, you can always think about like any examples which you find useful, right? And using that way, you can do that. Now, all of you should have this class lecture, right, with you. If you go to the very last pages, you will see kind of what I have just discussed here in terms of Q and H, and how can you find the power and efficiency for the combined pumps. I also give you some simple steps. Whenever you are lost, you can always come back here and check, okay, what should be the next steps, okay? Okay. Are we ready to do some mathematical problems?
We were born ready for this.
Oh, great. We will work with class example 10 and 11. Do you have that?
I don't have 10.
You don't have 10? Here. So 10 and 11, sorry, not the 9 and 10. Okay. So who will read the class example 10? Not Connor, he already did that. Anyone else? Read the class. Yes, do that.
These pumps are arranged in series. This one?
Yes.
A system having a total static head of 80 feet. The pipeline provides a 6-inch diameter of 212,000 feet length. The miners lost 20 times the velocity head, considering F is equal to 0.022. Using the DW equation to make a loss, determine the operating head of discharge, the efficiency of the combined pump, and the input power, regular power for the combined pump.
Thank you very much. So we have two pumps in a system. Now here, I will just make one correction here. The picture you have, it looks like it's one open reservoir, one pipe end, but let's make that two open reservoirs. So this will be 0.1 and this will be another surface, which is 0.2. And they have two pumps and they already told you it's arranged in series, okay? So this is pump A, this is pump B, and for pump A and pump B, these are the pump characteristics curve, the table 1, okay? If you look at the pump impeller diameter, one is 8 inches, one is 10 inches, and the speed is different also. So these are the total pump characteristics curve for A and B. And now this is the system you have. Now for this system, you need to develop a system curve. Once you have the system curve and pump characteristics curve, you can calculate Q and H at operating point You need to find the combined efficiency. It simply means after adding these two pumps together, what will be the combined efficiency and the combined power. Okay, so that's what we will do. Now, since we need to find operating head and discharge, that is the very task, first task, that means we need to develop two curves. But the good thing is pump characteristics are given, so you don't need to develop, you just need to plot that, or maybe it's given. You just need to develop the system curve. Okay, that's what we will do. Does that make sense?
Yes, ma'am.
Okay, so let's start working on that. We have few steps, like I tried to break down the total problem into 5 or 6 steps. We will go through each steps. So the very first one is pipes are connected in. That is very important to identify because that will tell you whether the head will be same or the Q will be same. Okay. Now the second one, computation of system head curve. Now computation of system head curve simply means from the system you have, you need to come up with the equation which will express the relation between head and Q. Okay, so we know the equation is since we are using two open reservoir system, that is the equation. You can develop that from energy equation also if you want. Now for this one, what is the delta Z? AD, right? And the head loss, they said that you need to consider minor losses. So what you will do, you will say major this one, right? So AD for major head loss, I asked you to use the Darcy-Weisbach equation. So either you can say FL over dV square over 2G, or you can go back to that table 15.2. Do you have table 15.2? And for the minor loss, KL V square over 2G. So I have the table 15.2 here. Since we are using Darcy-Weisbach equation, we will use, like there are two options. One is the first one and the second one, because all the Q we are having, they are in GPM. But I always prefer to use everything is in the like standard unit so that I don't have to think, okay, where I should convert or where I shouldn't. So I will prefer to use this one, FL 39.7 d to the power 5. Okay, so let's use that. FL 39.7 d to the power 5, and since we are using Darcy-Weisbach equation, it should be Q square, right? So I will just make a note, table 15.2. Okay. Now AD plus what is F? L is 1200, right? 39.7, D is 6 inches, so I need to convert that. Now, obviously, I don't want to work with V, and you know my next question, how can we convert V to Q? And the answer should be, we use the continuity equation, Q equals to AV, so that will give us the Q, right? Now, whatever summation of KL, I don't know anything about summation here, like any minor loss coefficient here, how to find that? Is there any information given in the picture or in question statement? It says that with a minor losses 20 times the Velocity head. Velocity head means what? V square over. So it says that 20 times velocity head. That simply means summation of KL is what? It's the 20. Okay. So I will add 20. You know how to calculate the area, pi r square, right? So in the next slide, you will give me the number for these and these. Okay. So I will have AD plus something Q square plus something Q square. So give me this. Oops. For the first part, you should get something close to 20. For the second part, you should get something close to 10. Not exactly 10, not 20. Like for this part, you should get something close to 20.
I got 80, like the 80 plus that, I got 82.65. 21.28. Oh, wait.
Yes. Did you divide by d to the power 5?
I forgot to do it.
Okay.
I got 101.2.
For this part,
Yeah, if you add 80 with it.
you can't add 80 because 80 is 80. There's nothing. And something is with Q. So check, calculate that again.
21.27.
That sounds reasonable. That's what I got. Anyone else got that? Okay. So I'm going to the next slide here. Pump AD plus, you got 21.3.
Yes.
And what is for the second part? What number you got?
Divided by
2G divided by A square also. There's A. What number you got? Anyone else?
what's the A value?
A pi r square. So it will be,
Yeah, but you have two different pumps.
okay. So this system is for actually for pipe, not for the pump. So you will use the pipe diameter, which is, it should be 3, right? Pump is for pump characteristics curve. Pipe system curve is for only for the pipe. That should be the A. Okay, anyone else has any number for this one?
I got 6.3.
Maybe you need to divide your number by A square. Did you do that? It should be something close to 8. 20 divided by 2G. G will be what? 32.2. And the A square, not A. It's Q over A square. So you will divide that, what? It should be 22G. This one. 8 point what? That sounds right.
That's what I got.
Okay, great. You got some confirmation. 3q square, 8 point what? Oh, okay. Now finally we have AD plus 21 plus 8 is 29. 36 or something like that, right? Okay, so that is that a system curve or pump characteristics curve we developed here? It's the system curve because you are using all the pipe diameter length from your system here, right? Okay. Once you have the system curve, what should be the next step? You have the curve, but you need to get the operating point. So you need to
Build the table.
another curve, yes. At the same time, you need to plot that, right?
Yes.
Now, for any Q value, like you will pick some Q values to find HP, right? Or H pump actually. Now you can select any Q values, or another practice you can do, you can just take these Q values here, okay, and find the HP. We will start from this point. Please make sure you bring your this class example and the next one, okay? And did I tell you that most probably next Friday, not this Friday, next Friday, you may have your test 2? Okay, or maybe I told that to section 1.
You told that to us.
Oh, okay.
Next class, I won't be here, so you